Okay, so today, you're laughing. I haven't even started talking yet. Today is the last day before Thanksgiving. Woo! Go Chefs. America? Really? So, really quick, I'm not going to spend, I know you guys, your heads are elsewhere, as is mine, so it's going to be super short. We're going to do a really quick description of why things dissolve in other things, and then a couple units of concentration problems, and we'll be done fairly quickly. So first thing I want to talk about, did y'all learn in pre-AP that, or regular, that polar substances dissolve polar substances? Yes. Don't lie. I'm going to say your name on the tape again. And nonpolar things dissolve nonpolar things, and they might have even used the term like dissolves like. Please don't use that term on the AP because it's not a reason. Like dissolves like is not a reason why things that are polar dissolve polar things and vice versa. So I'm kind of going to give you an explanation here. I have some models for you guys to see. It'll be hard for the people at home to see, but oh well. They need to see me in person. It's much more exciting than just hearing my voice. No commentary, Thomas. I don't know what you're saying. So we're going to start with polar-polar mixtures. Rather than ionic, go ahead and change this to say we're going to mix ethanol and water. So in order for things to mix, what has to happen? So I have these models here. We'll say this hand has ethanol in it, and this hand has water in it. Okay, they're both what kinds of substances? Polar and nonpolar. Polar, what's the intermolecular force that both ethanol and water have? Hydrogen bonding, dipole-dipole, specifically hydrogen bonding. So in order for these to become miscible and come together, what has to happen? Oh, that's weird. Whoa. What has to happen to these sets of molecules in my hands? Not break their bonds. You're right, though. No. These have to overcome their own intermolecular forces, right, in order to then mix with these guys. And these guys have to overcome their intermolecular forces in order to mix with these. Make sense? Okay, so that's what these up arrows represent. This represents the amount of energy you have to put into a system in order to overcome the intermolecular forces. So hydrogen bonding has to be overcome. That takes some energy. Hydrogen bonding here has to be overcome. That takes some energy. So why would they become miscible? What would make them then mix up? Energy is required to overcome. What would make them mix up? Well, what needs to happen is these water molecules need to be just as attracted to the ethanol molecules as the ethanol molecules are attracted to the water molecules. If they are, mixing's going to happen. Why? Why does mixing happen? Let's talk about the universe and order and disorder. What's that called? Entropy. Things tend to disorder, right? Correct? So mixing is going to be more of a disorder. However, it won't happen if there's an energy deficit. So in order for it to happen, we need to have, this is just really messy. We need to make sure we're getting the same energy back. So because water is polar, it's going to be attracted to the ends of the ethanol as well as it is to itself. So hey, nature tends to disorder, let's mix. Why not? And that's what happens. Okay, does that kind of make sense? So what do you say? Why do polar things dissolve polar things? Polar solvents will dissolve polar solutes because the solvent is just as attracted to the solute as it is to itself. Does that make sense? That's your safe way of saying it. The solute is just as attracted to the solvent as it is to itself, so hey, why not mix? Got it? All right, so what about nonpolar stuff dissolving nonpolar stuff? Kind of the same situation. What type of intermolecular forces are in nonpolar solvents? London dispersion and solute, kind of the same thing. We've got to overcome London dispersion forces. Not real attracted to each other. It doesn't take much energy to put in. So why not just go ahead and mix with the others, because they're just as attracted to each other as they are to themselves. So we're going to get back the same kind of energy once they re-attract. And that's it. Done. Dissolution happens. Miscibility happens. So again, I'll write the statement. Nonpolar solutes dissolve in nonpolar solvents because they are just as attracted to, I'll say the other as themselves. Okay, so let's look at the bad situation when dissolving won't happen. And again, just change this to ethanol. I'll talk about ionic stuff in a second. Say we're trying to mix ethanol as a solute into a nonpolar solvent like oil, whatever. Doesn't matter. So ethanol, hydrogen bonding, right? Super, super polar, positive, negative, partial charge ends. Very attracted to itself, right? Tough to overcome those intermolecular forces. So we got a pretty big energy that we have to put in. Here, to separate something that's London dispersion like oil, not too tough to do. Is ethanol attracted to oil? Is it? Maybe a little, but not as attracted as it is to other ethanols. So why would it want to go mix with things it's not as attracted to? It's just going to stay as itself, okay? And ethanol, and oil or whatever non-polar substance we're talking about is going to stay it's as itself, and that's why we get, you've seen oil and water mixed, right? You get that layering. It's just not going to mix. It's not miscible, okay? Because the energy they get back, this is just not excited. Why would it want to hang out with boring, non-charged stuff like oil, okay? So that's how you do that. So let's go to the problems then. Explain the concept like dissolves like. Like dissolves like. And I'm going to repeat myself again. Polar solvents dissolve polar solutes because they are just as attracted to the solute as they are to themselves, and vice versa for nonpolar. Vice versa for nonpolar, nonpolar. Okay, there's no energy loss there. Now here's going to be a typical AP question. Decide whether hexane, what does that look like? C6H14, it's a straight chain of carbons. Or liquid methanol. Methanol's 1C, so there's our methanol. Is more appropriate for grease and potassium iodine. So basically we're coupling up. So let's look at hexane, C6H14. What kind of intermolecular force, is this polar or nonpolar? Nonpolar. Its intermolecular force is London dispersion. Which one is that going to dissolve? Well, it wants to dissolve something nonpolar. That grease, look at all those C's and all those H's. Lots of nonpolar action going on there. Okay, So this is going to dissolve your hexane. I know we haven't really talked about ionic compounds and how they dissolve, but I want you to treat these ionic compounds pretty much like polar compounds, in the sense that once these ionic compounds hit water, for instance, if they're soluble, they dissolve into ions, right? Okay, so they have positive and negative ends that can be attracted to the positive and negative partial charges of water, of any other polar stuff. So ionic compounds, because they have ions, the ions are attracted to polar ends of molecules. So water will go in there and wiggle in between a lattice, and it'll break the lattice and create ions. That's why salt dissolves. Well, soluble salts at least. Ends of molecules. And that only happens with the polar molecules. Nonpolar molecules don't have that positive negative end, so they can't wiggle in there and do the same thing. So what's going to dissolve potassium iodide? Which one, hexane or methanol? Methanol. Because methanol has what type of intermolecular force? Hydrogen bonding, and it's polar. So kind of treat ionic as polar in the sense that polar things dissolve ionic compounds, not nonpolar. Go drop some salt and some vegetable oil and see what happens. Nada. Okay. Got it? Okay. Let's move on to units of concentration. All right, so you'll need your calculators. You've seen all of these before. This year you are responsible for knowing them, though. They are in the AP equation sheet, but I don't care because they might even show up in the multiple choice, some of the multiple choice questions, and you need to know molarity and molality and mole fraction and percent. I mean, these are just really basic concepts. Weight percent is your weight of your solute over the weight of solution. You got to watch for these denominators on all these different equations because some of them are solution and one of them is actually solvent, so just be careful. Weight percent is used common in medicine. Have you ever been to the hospital or seen someone in the hospital that has like an IV bag that says 4% saline or something like that? That's referring to weight by percent. So if we're say 4% saline being sodium chloride, how much sodium chloride do we have in how much solution? 4 grams in 100 grams of solution total. Okay, so how many grams of water will we have in there then? 96. Jasmine has said 95. Anyway, so it's important to realize that this is the weight of both the solute and the solvent. Okay, and then you multiply by 100 to get a percent. Mole fraction should look familiar to you. When did we do this? Earlier, yes. What specifically did we find the mole fraction of? Mixtures of what? Remember Raoult's law? Gases. I'm going to pause this so I can yell at my class. Excuse me. Okay, let's continue. Mole fraction then is moles of whatever you're looking for. It might not be the solute. And this is the thing. It could be moles of solute or solvent. You can find mole fraction of either, and I just want you to understand that. It can be moles of mole fraction of solvent or solute, and it's going to vary depending upon the problem you're actually doing. But if you're trying to find the mole fraction of the solute, then it's moles of solute over total moles of solution. You add up the moles of solute plus solvent. All right, molarity, you better know molarity, moles per liter of solution, moles of solute over liters of solution. Again, the units on this are moles per liter. I don't want you to use a capital M as your unit. I want you to use moles per liter. And revisiting molality, I'm sure you all recognize this. This is moles of solute. This is the one that's different, over kilograms of solvent alone. All the others are total solution on the bottom. This is solute kilograms alone. of just that. So let's practice some problems and then we'll be done. Calculate the molality and mole fraction of HCl for a solution which is 37.1% HCl by weight / mass. All right, so we want to calculate molality. When we're calculating molality, what are we getting? And I want specific moles of what over what? More specific than solute. What's the solute in this problem? HCl over kilograms, and if it doesn't say, you assume what solvent? Water. So we need to find that information. If we're finding mole fraction of HCl, what are we looking for? Moles of HCl over all moles, which is HCl plus moles of H2O. Okay, so which one do you want to do first? Well, actually, let's take a look at the information they gave us. They told us that it's 37.1% HCl by weight. What two pieces of information can we get from that? Let's pretend 100 grams. So we have 37.1 what? Grams of HCl compared to 100 grams of water? No, 100 grams of solution. That doesn't help me. I want water specifics. So 62.9 good grams of H2O. So by subtracting the 37.1 from 100, you now have grams of everything. So what do you want to do first, mole fraction or molality? Molality. Okay, so to do molality, we first need moles of HCl. So I'm going to convert this to moles of HCl by saying for every 1 mole, I have about 36.5 grams. So go ahead and give me, on your calculators quickly, that number of grams, please. 1.02 moles. Okay, that's moles of HCl. Good. Let's go to the next one then. And we're doing molality, sorry. So we're going to plug in 1.02 moles here. Do we have kilograms of water? I know grams, 62.5, so what are kilograms? 0.0629. And then we're going to multiply, oh, this is not percent. Then we're going to just solve for molality. And what do we get? To three sig figs, please. Louder? 16.2. And it's moles per kilograms is our answer. So that's our molality. Okay. Now let's move on to mole fraction. I know moles of HCl is 1.02. What do I need to finish this problem to get mole fraction of HCl? Moles of water. So I'm going to multiply this for every 1 mole. I've got 18.02 grams of water. How many moles of water does that give me? 3.49. Since this is the mole fraction specifically of the solute in this case, it's going to be a small number, 0.1, 0.2, 0.3, something like that. If we're doing mole fraction of solvent, that's supposed to be the largest component of a solution, the solvent is. That's why it's defined as a solvent. So it's going to be bigger, like 0.7, 0.8. But this is a solute, so we can expect a small decimal, and what is it? 226. No units, just a decimal, done. That is mole fraction. Got it? Okay, next problem. If the density of the solution described just above is 1.18 grams per mil, so we know 1.18 grams of that above HCl solution is equal to 1 mil. Calculate the molarity. What is molarity? Moles of, specifically in this case, HCl over liters of solution. So what do I have from above that I can use? Moles of HCl. You need to be really careful here because that many moles of HCl came from how much solution? 100 grams of solution. That's important. So we can go ahead and plug in 1.02 here, but we need to, using the density, convert the 100 grams to, we need liters. So I'm going to start my dimensional analysis over here. I'm going to start with my 100 grams of solution. Okay, my density, I'm just going to go and plug in. For every 1 mil, I have 1.18 grams. Okay, but I got to get to liters, right? So for every 1 liter, I have 1,000 milliliters. So what is my liters of solution? 3 sig figs. 0.0847? 0.0847 liters. So I'm going to plug that in here. 0.0847 liters. And that's going to give me a molarity of 3 sig figs. 12.0. And the units on that, moles per liter. Isn't that fun? Are you ready for the double sexy problem? This is the best problem ever. A solution of ethylene glycol. Does anyone know what ethylene glycol is? What? Not spray paint. It's close. A lot of people are accused of killing neighborhood animals with it. Not rat poison. It has a sweet flavor to it. That's why the animals will not paint thinner. Nope. Nobody knows? You put it in your cars. Not gasoline. Antifreeze. The girls got the boys on that one. Antifreeze. Learn that. That's a good one to know. That's a good Trivial Pursuit question. Ethylene glycol is antifreeze. Yeah, and they even have, there's even some winemakers back in the 80s that got busted for putting a few drops in the wine to make it a little bit sweeter. Not enough to hurt anybody, but it's still, it's like when you absorb it, supposedly when it breaks down, it creates some sort of neurotoxin in the body, and it's pretty intense stuff. So don't drink it and don't give it to cats. Another life lesson from Demo. So we have the solution of ethylene glycol here, which is they're meowing, 6.77 molar. What does that mean? 6.77 moles of what? Ethylene glycol. I'm going to call it EG just for ease sake. Moles per what? A liter of solution. And it has a density, this molarity solution has a density of 1.05 grams for every 1 mil. Calculate the mole fraction of ethylene glycol. So if we want the mole fraction of ethylene glycol, I need moles of what? Moles of ethylene glycol over moles of EG plus moles of what? Assume water, H2O. All right. Wow, what are we going to do? Well, don't we know kind of moles up here? So if we're going to assume we have this many moles, and if we're going to put that number here, we have to assume and carry through how many liters of solution? Assume 1 liter, so we're going to have to carry that through. This is a great problem, and I want you to think about it. I'll probably end up pausing the video here, but I want to know, how am I going to figure out moles of water? Because I know moles, this is going to be 6.77, and this is going to be 6.77. Where the heck am I going to get moles of water? Any ideas? Okay, let me pause and get the right answer, then I'll let somebody say. So Jasmina redeemed herself and told us how to do this. She suggested going ahead using the 1.05 gram per mil density and converting that using the 1 liter of solution to total grams of solution. Once we have total grams of solution, I guess I should write this down. Use density to find grams of solution. Okay, assuming 1 liter. We got to assume 1 liter because that's what our moles is based on. And then we're going to convert moles of EG to grams. And then we're going to subtract grams of EG from grams of solution to get what? What does that give us? Grams of, do I need grams of water? No, then convert that. I love this problem. This is super sexy. This is awesome. Cough, cough. You might want to know how to do this problem. All right, so let's go ahead and do this then. That's our instructions. So starting with my 1 liter of solution, I want to convert that to grams. Well, I know that there are 1,000 mils in 1 liter. I need to do that first. And then using the density, for every 1 mil, I have 1.05 grams. So what is the grams of a liter of my solution? What are the grams? 1,050 grams is the mass of my entire 1 liter of solution at 25 degrees Celsius, but we won't talk about that. And then I'm going to subtract that. From that, I need the moles of EG. So somebody out there has to get me that molar mass, please, while I set this up. Wow, you're on it. So we got 6.77 moles. For every 1 mole, 62 point what? 62.08 grams. All right, so what is my grams of this EG? I'm deaf. Say it one more time. 420.3. So I subtract that to get me grams of H2O. And what are the grams of H2O? All right. So can I use that? Nope. I've got to take that 629.7 grams and convert that to moles. So for every 1 mole of H2O, I have 18.02 grams. So that's 34 point. So let's just say 35.0. 35.0 moles. That's a lot of moles compared, but again, that's the solvent. We should have more than we do of the solute. All right, so I have 6.77 over 6.77 plus 35. So what is my mole fraction of ethylene glycol? 0.162. Voila. Isn't that an awesome problem? Yes, Demo, that's awesome. All right, no questions? Happy Turkey Day.